just as a quick reminder of our percentile definition, we're going to use this illustration. And so the number 1,592 is going to be the 35th percentile of a data set if you have at least 35% of the values less than or equal to 1,592. And that leaves 65% of the values greater than or equal to 1,592. Again, so the 35th percentile is just the number separating the bottom 35% from the top 65% of any sample or population. All right, and we're going to use the shorthand P35 to denote the 35th percentile. Okay, now given that, let's take a look at an example.
In this episode, we're going to talk about the chi-square distribution. So I want to remind you, all right, we've already talked about these in class. The way we tell one chi-squared from another by its degrees of freedom, which for us will be a natural number. It's defined on the interval from 0 to infinity. So unlike the normal and t distributions that go on forever to positive infinity and to the left to negative infinity, chi-squared scores are always 0 or higher. It's a skewed right distribution. All right, so meaning you're going to have a peak on the left and a long tail on the right. You have a few high numbers skewing the mean above the median. Now, turns out that our mean on the chi-squared is equal to its degrees of freedom. And this is a critical point you need to remember because it's your only landmark on our horizontal axis between 0 and infinity. Now, like I said, it's a skewed right distribution. So the mean of a chi-squared is going to be to the right of our mode or our peak. So as we enter the downslope on these graphs, somewhere to the right, about halfway down the slope is approximately where the mean will be. Okay. And finally, take a look at that standard deviation. It's 2 times the degrees of freedom. So as the standard deviation is increasing with the degrees of freedom increasing, the graphs are going to get wider and wider because the standard deviation tells us how spread out we are, that average distance from the mean. And of course, if the graph gets wider, it has to get shorter because the total area under the curve is always 1. Okay, so let's look at an application. We have a chi-square distribution with 17 degrees of freedom. We're randomly going to pick a value from that population. We want to know probably the value we pick is less than or equal to 22. So, you know the drill. First step, draw the appropriate graph. This is a skewed right graph that starts at 0, so it'll look something like this. Now, at this point, we want to label the legend. So again, so everybody knows this is a chi-square with 17 degrees of freedom down there in the bottom right-hand corner. We're going to label the mean. 17 degrees of freedom says the mean of the chi-squared will also be 17. Okay, and again, it's somewhere here on this downslope in this approximate neighborhood. Again, this is just essentially a rough graph, and your hand graphs will always be rough. Okay, the other key point on a chi-square distribution is 0. Right? There is no chi-squared score that's ever below 0. Now, we next want to look at our specific problem. We want the probability that our chi-squared scores are less than 22. So we're going to find 22 on the horizontal axis. All right, so 22 is going to be over here to the right of 17. All right, but not too far because, again, if you think of that mean of 17, all right, approximate the distance from 0 to 17. We don't want to go that far again to the right. That would be all the way out to 34. So we want to go somewhat to the right. And 22 will be somewhere in this neighborhood. And we're going to shade in the area in between because we want 22 or less. We want the chi-squared score. That's your variable. Think about what you want it to do. You want it to be less than 22. All right. So, final thing. Choose our appropriate tool. And recall, when we were dealing probabilities and we had a normal distribution, we did normal CDF to find probability. When we had a t-distribution, we used a t-CDF to find probability. But now it's chi-squared distribution. We're still going to use the CDF, but the chi-squared CDF to find probability. So, to find this probability, we have to tell it the lower and upper limit of the region we want, like all of our CDFs require. So, from our graph, we can see the shaded region, lower limit 0. Okay, chi-squared scores never go below 0. Our upper limit is 22. We want the probability that we're somewhere in between. So lower limit 0, upper limit 22, degrees of freedom are 17. We put that in our calculator and we should get out approximately 0.8153. And if we look at that blue shaded region, that's about 80% of the graph roughly. So that seems to at least be reasonable. Clearly the shaded area is more than half, so we're expecting some answer bigger than 0.5. But it's not everything, so we're not really expecting something closer to 0.95, 98, 99. So again, always check your calculator to make sure that the number it's giving you seems reasonable.
So we're going to assume that the length of UT students' drives from campus back home in miles can be approximated with the chi-square distribution with 50 degrees of freedom. And we want to know the probability that a random UT student drives more than 75 miles to get home. So once again, I know it's a chi-square distribution. First thing I'm going to do is draw the graph. Okay. So I want the probability that my chi-squared score is greater than 75. So my chi-square graph starts at 0, right? Long tail on the right-hand side. And chi-squared with 50 degrees of freedom tells me the mean is going to be 50. And we want the probability that our chi-squared score, or our number of miles, is higher than 75. So over here on the right-hand side, we're going to shade in everything to the right of 75. And again, these graphs are just to give us an idea of exactly what's happening and to help us use our tools properly. Okay, so now, to find this probability, we're going to use the chi-squared CDF. Okay, and again, we got to tell it the lower and upper limit of the region we want and the degrees of freedom. So we're going to do the chi-squared CDF from 75 to infinity, okay, with 50 degrees of freedom. And when we do that, we're going to get an answer of 0.0126. Okay, so 0.0126 is the probability that a random student drives more than 75 miles to get home.
Now that we've gone over probability with the chi-square distribution, let's talk about percentiles. So we want to find the 90th percentile of a chi-square distribution with 28 degrees of freedom. So again, that little P90, that notation is saying we're looking for the value from this world, the chi-squared score, that is bigger than 90% of all chi-squared scores. Now, another way to look at that again is we're looking for the chi-squared score, where the probability that another random score would be less than that number, P90, is going to be 0.90. We need a 90% chance that random values will be less than this unknown number. So we're going to draw our graph. Again, chi-squared graph, skewed right, put in our legend, label it so everybody knows it's a chi-square with 28 degrees of freedom. Our key points, the mean is 28 because we have 28 degrees of freedom. Minimum score is 0. Now, specific to our problem, we want to find the 90th percentile. And again, the 90th percentile of any population is going to be a big number relative to the other values in that population because it's bigger than 90% of the values in that population and less than only 10%. So somewhere over here on the right side of our horizontal axis is a mystery chi-squared score. Okay. Now, there's only 10% of the values that need to be higher. So again, we're going to use our appropriate tool to find the score that fits this situation. But before I ever go to any tool, I know that this number has to be bigger than 28 because our mean is 28. And a little over 50% of the numbers are less than the 28. Remember, this skewed right part of the chi-square distribution says our mean is a little higher than the median, the 50th percentile. So at this point, we're going to have to go to our chi-squared chart, except for very, very few of you. A few of you do have an inverse chi, but 99% of you or more have to use the chi-squared chart. Okay. Important to remember that on the chi-squared chart, the way it's designed, you have to look up the area to the right of the critical value. Again, remember, the critical value is just the term we use for the value, the t-score, the chi-squared score, the z-score that we're looking for, okay, that fits our situation. So when I look at this graph, I'm looking for the 90th percentile. The area to the right of that needs to be 0.10. And so when we look up 0.10, drop down to 28 degrees of freedom, we're going to find 37.916. And just to make sure we're clear on this, let's take a look at the chi-squared chart. So you want to get out your own chart so it looks nice and clean and easy to read the numbers. Our area to the right of our critical value was 0.10. We wanted 28 degrees of freedom, so we're going to drop down here to 28 degrees of freedom. And at that point, you should see the 37.916. Okay, so that is the 90th percentile of our chi-square distribution with 28 degrees of freedom.
So let's look at a chi-square percentile example. Okay, so again, we're talking about the length of drives from campus back home for UT students. We're going to assume that they have a chi-square distribution with 50 degrees of freedom. Okay, and we want to know how many miles from campus is it for the 10% of students who live the closest to campus. Okay, so closest to campus means short drives, not long drives. So we're looking for the 10th percentile. And so the first thing I'm going to do is draw myself a chi-square graph. Again, from 0 to infinity, the mean is 50 because we have 50 degrees of freedom. We're looking for the 10th percentile, separating the shortest 10% from the longest 90% of drives. Okay. Now, as you can see from the graph here, okay, I'm claiming that that 10th percentile is going to be 37.689 miles. So how are we going to get that? We're going to have to look at the chi-squared chart. Now, when you use your chi-squared chart, at the top it says the area to the right of the critical value. So in this case, we're going to look up 0.90 because that is the area to the right of the point we're looking for. And that's where we're going to get the 37.689 miles. And that's the chi-square distribution. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!